Welcome, everyone. Thank you for being here. This will be recorded for who hasn't had the chance to watch this live, let's say. Welcome to the fourth lesson of our masterclass that we've been preparing with Dan. And just a quick recap on the previous lesson, we went through the access control mechanisms. We saw how to prevent common attacks like reentrancy attack with the reentrancy checks and effects pattern. We looked also at the secret sauce of Ethereum success through the ERC tokens, and we also had an introduction into oracles. In this lesson, we'll be looking at upgradability of smart contracts and also libraries. Why these two concepts, and it will take most of our time, hopefully we can do it in time, is because we know that smart contracts and blockchain environments in general are immutable. You can prepare them in ways that they are configurable, yes, but in general, you can't change the bytecode of a smart contract once it's deployed. So why upgradability? Upgradability is needed in many real-world scenarios whereby a smart contract would require an upgrade, a change, maybe a bug fix, adding new functionality, or performing a hotfix on the go, like something incredible can happen. Even pausing a contract itself is a sense of upgradability. And to do so, many patterns have been discussed, evolved since the inception of Solidity. And out of these, we'll be looking at the imminent and most battle-tested, audited standards, starting from what isn't really an upgrade, but we call it like a parameter upgrade. So what is a parameter upgrade? We've seen many contracts during our course where we have state variables that can be changed after deployment. Those are known as parameter upgrades. It's like, I don't know, changing a fee, maybe setting some max limits, switching out some addresses. So you're not actually changing the core business logic of your smart contract, but you're tweaking parameters in order that the output of your functions can change, can alter in time. This is cool because you don't have to deal with super complex patterns of upgradability. It's simply creating your contract to be as flexible as possible in a parameterized way. So no need of so-called proxies that we'll soon see what those are. Paraj, one second, let me admit this. Okay. So the caveat, though, to this is that if you actually have major bugs or need to refactor or add new functionality, it's not possible because your contract is already deployed, your bytecode is not changeable, but you can only tweak around those settings, those parameters. In fact, let's look at a quick example on a parameter upgrades contract. For example, here you have two parameters, the owner and a fee, let's say. And through the common setters, you're able to tweak around these parameters and maybe changing the fee, change the output of a deposit function in your sample contract. But as we said, this does not add the possibility to add obviously new functionalities or fix any underlying issues. And that's where a new kind of upgrade, let's say, way comes in place, the so-called social migrate upgrade. Remember back in 2017 when we had like the ICO boom, we had even in 2020, 2021, so many new protocols, NFT collections, and every so often they would come up with the necessity of upgrading or migrating to a version 2. That's exactly the concept of social migrate. It's a non-technical upgrade approach. It allows basically the dev team, the protocol team, to completely change the contract to which you need to interact with, but it requires complete engagement and complete collaboration with your community because you have to involve your community to switch. You need to involve your developers to point to the new contract. And out of the pros of this, it's obviously no complicated code for handling upgradability, just redeploy. But the key nightmare to this, obviously, is the user experience. The state migration. You need to purely rely on the cooperation of your developers, your users, and state migration could become also very delicate because you're basically migrating the state from a completely different contract to a new one. So that not only entitles maybe a lot of gas costs to save the new data to the new contract, but you can also mess things up if not correctly migrated. In fact, the folks at Trailbits back in 2018 put together some key concepts and best practices when performing a migration, if you guys want to have a read on this. But now let's look exactly at what has become one of the key standards in upgradability because of the fact you're able to maintain the same address by actually changing, replacing, modifying the core logic of your architecture, of your smart contracts. How this works is through the use of a so-called proxy. Think of the proxy like a stand-in actor in a movie. The star, the actual, let's say, actor, can change, but because he has the same wearables, he has the same makeup maybe, the audience, who are the users, actually see the same character, which in this case is the proxy, but behind the scenes, the actor himself can change. So this is just a way to explain what proxies are. So in general terms, a proxy is a single contract that holds data, our storage, and an implementation contract instead is a separate contract. So we have at least two contracts, a proxy and an implementation contract, whereby the implementation contract actually holds the logic, the business logic to perform in our protocol. This means that if we replace the implementation contract with a new contract, the data doesn't need to be migrated because it's still inside the proxy, and the proxy just has to point to the new implementation contract. How this happens is through a magical low-level function in Solidity, which is the delegate call function. Delegate call, I call, is the secret source of proxies in this case, and it's, again, a low-level function where the code in the target contract, so our implementation contract, is executed in the context of the calling contract, so the proxy in this case. In simple terms, if I basically delegate a call to a function in contract B from a contract A, I'm actually performing the contract B's logic in the context of contract A. Also, one really important thing of delegate call is that we're preserving those global variables known as the message.sender, so who is the actual caller of the proxy, and the value. So the value, the amount of ether or native currency we're performing the transaction call. Delegate call differs from call, which in the first case, so for calls, we're invoking a function on a contract, and it's executing in the context of that contract. So for example, if I see this diagram here, me, a user, which can even be another smart contract, performs a call to this contract here. What happens is if this contract then performs a call to our target contract or our implementation contract, what's happening is that we're executing the code in the context of the target contract. And the message.sender is not the EOA, but it's actually the caller contract. Instead, if we perform a delegate call, what happens is that the exact call is forwarded. Imagine like a forward, instead of being the caller contract, it's directly forwarded to the target contract and executed in the context of the proxy or the caller contract, meaning that if we perform any storage updates, those are updated in the proxy itself and not inside the target contract. Therefore, enabling these standards and these use cases, such as proxy upgrades and the upgradability that allows, and we see every so often in modern protocols, whereby there's a single address and that single address can point in time to new implementations, whether it's new features, fixes, and whatever is the reason to point to a new implementation. And before we look into the well-known proxy standards, just some recap on some proxy terminology so it's not too confusing, let's say. The implementation contract, as we can see here, is a smart contract that holds the logic of our protocol. This means that when we perform an upgrade, we're actually changing the implementation contract. The proxy instead is another smart contract. This is the contract that actually holds the address with which developers and users are interacting with. And the proxy contract points to the correct implementation contract to which it delegates calls to the implementation contract. Meaning that when we perform an upgrade, we're actually pointing to a new or separate implementation contract. A user is simply an EOA or a smart contract that calls the proxy, and the proxy delegates calls to the correct implementation contract. And an admin is an individual or a group who is allowed basically to perform upgrades to our protocol and therefore switch around the implementation contract from one to another. So what is the first most common battle-tested proxy standard? It's the so-called transparent proxy. The transparent proxy, like we've talked about until now, has a single proxy contract and it delegates calls to an implementation contract, so nothing new. But the key feature, let's say, of the transparent proxy here is the differentiation between an admin and, let's say, any user. The admin is a specific user that is obviously allowed to perform upgrades, but the upgradability is inside the proxy. So the logic is inside the proxy itself. We'll see why this key difference, because it obviously is different from the other standards that we'll see soon. Why is it transparent? It's transparent because all these complexities are transparent to the user. It's transparent to user code, but it's actually visible to the admin. In fact, what happens, we'll see soon in the source code, is that the proxy performs checks whether the user is an admin or not. And if he's an admin, then he can perform the upgrade. And if he's a user, he directly forwards the call to the target contract. Obviously, the pros to this is that, as we said, it's a well-tested and widely adopted. It's one of the first standards that has been adopted and audited in time. Its implementation is quite easy, but the main con to this is that there is a bit of overhead in the proxy due to the double, let's say, selection between the admin and the users. So without further ado, let's quickly dive into our source code. So this repository I'll be sharing, it holds both the access control, EIP 712, ERC tokens, etc. that we saw in the previous lesson, also the reentrancy attack mechanisms. And in this lesson, it's holding what we see around proxies and also libraries. So inside the proxy folder, just open proxy and then transparent proxy, and we can see all the contracts involved with this standard. Inside the transparent upgradable proxy, this is basically a fork of OpenZeppelin's implementation of this standard. And we can see that it inherits from the base ERC standard for proxies. This standard is the bare-bone proxy standard, which simply delegates calls to the implementation contract without having to perform any checks prior to delegation. Instead, with a transparent upgradable proxy, what happens is that here we are actually performing not only an instantiation of a proxy admin, which is another contract, but also a check in the fallback function if the user is an admin or not. And this is basically the overhead I was talking about before, because the upgrade logic is inside the proxy rather than the implementation contract. So looking at the deployment in the constructor, what we're passing here is simply the logic contract, so the implementation contract to which the proxy is going to point, the initial owner, so this is the EOA of the owner of the proxy admin contract, and then some additional data. This data is basically data required to initialize post-deployment of the implementation contract. Because with proxies, we will see with our test suite cases, is that we first have to deploy the implementation contract, and then we need to attach or point the proxy to that implementation contract, meaning that the initialization of the proxy storage needs to happen post-deployment of the implementation contract, which is a key difference with simply deploying a contract and having everything initialized in the construct of the implementation contract. But in the case of the transparent proxy standard, we are instantiating this proxy admin contract, which we can see here. It's a very simple contract. It allows basically the owner of this contract to perform an upgrade of our proxy, pointing to a new implementation address. And then what we're doing here is specifying the admin being the address of this contract here. And in the fallback function, so fallback again is a Solidity special function that is invoked when specified a function that is not actually part of the bytecode of the proxy. Again, because the bytecode of the functions is actually inside the implementation, so it's not inside the proxy, meaning that if we interact with our proxy, that actual function is not present in the proxy bytecode. So it needs to fall back to this function and delegate the call to the implementation contract. And what's happening here is that we're checking if the message.sender is the proxy admin. As we said before, this is the overhead, let's say, part of the transparent upgradable proxy pattern. And if it is the admin and is also only calling the upgrade, then we are dispatching the call to upgrade by calling this internal function here. So you can also notice one key thing here is that if the function selector is not the upgrade to and call function, it would revert. So this is a particular implementation of the transparent proxy, meaning that the proxy admin can only upgrade. He can't directly perform actions by calling functions in the implementation contract. Instead, if the EOA or contract is not the proxy admin, then we're simply calling super.fallback, and this is the implementation of ERC 1967. So ERC 1967 is the barebone proxy contract that performs the delegation call. Everything happens, as you can see here, by calling the internal delegate function and by passing which contract are we performing the delegate call to. So who is the target contract? And the core function of delegate call happens in this assembly code here by passing the gas of the transaction, the implementation address, the call data, and this basically is the part where we're invoking the function in the implementation address and executing it in the context of the proxy. So this is an overview of the transparent upgradable proxy, and let's look now at the actual implementations. So we'll see in the test suite that we have, in this case, two implementations, an implementation A and an implementation B. In the case of the transparent upgradable proxy, we can only point to one implementation at a time. You can't point to two different implementations. But what we'll be doing is upgrading our proxy to point to a new implementation, which is implementation B, which not only overrides, redefines, the return value of version. So from implementation A, instead of returning A, it will return B, but it also adds a new function, which is get double value, allowing therefore our protocol to have a new function and also changed behavior in functionality, in this case of the version return value. So to see exactly how all of this is put together, let's quickly dive into our transparent proxy test suite. So here we have a series of tests around initial deployment, upgrades, and even edge cases. But everything resides in terms of deployment in this deploy proxy fixture. So first of all, we're defining who are the actors involved in this test suite. We have the first hard hat signer of our signers array, who is the owner, and then we have two simple users. This is for us to test cases whereby the action is being performed by the admin or by a simple user. Then we deploy the implementation A contract. Here we're also deploying the implementation B, but it's not necessary. We can just have the implementation A, because what we're doing here is deploying our proxy by pointing to the implementation A upon deployment. Then we're specifying who is the owner of the proxy admin contract, and we're also passing the 0x value here for initialization. This is because, as we can see here in the implementation A contract, we don't have any functions to initialize post-deployment. But we'll be seeing how this works with the next proxy standard. Once we deploy the proxy, we now need to obtain what is the actual contract address of the proxy admin contract. Because if we head back to the transparent upgradable proxy, here in the constructor, we can see that we're instantiating a new contract. It's the proxy admin contract. And to know exactly what this address is, we can use the get create address that Ethos offers, which is simply obtaining what the address is of that contract by passing the from, which is the proxy address, and the first nonce. And this returns the address of the proxy admin contract. So we can have the proxy admin contract here, and then we're returning from the fixture simply the proxy attached to the implementation A ABI, so we can interact in a type-safe way, and also the proxy attached to the implementation B ABI, so that once we upgrade to implementation B, we can interact with the added functions, which is basically only this one here. So get double value is the added function once we upgrade to implementation B. Having all this in place, now let's look at some actual tests. Once we deploy, here we're returning the proxy as implementation A, and we can expect that the version is the version A because we are pointing to the implementation A. In fact, let me quickly isolate this test suite here, run all these tests, and see that they're all passing, meaning that obviously also this one is passing. There you go. So should initialize with implementation A, that's passing. Also, we can test if setting and getting values works. We can test if setting multiple values works too. But in the upgrade part, here is where the magic happens with proxies. And in the case of the transparent upgradable proxy, what we're doing is actually interacting with the proxy admin contract. So this operation here, in reality, is like performing proxy admin.connect with the owner, where the owner is the owner of the proxy admin contract. Let me quickly import the owner here. So when you see a contract interacting with a function without specifying who is actually calling that function, it's like indirectly specifying the first hard hat signer of the signers array. So basically, this is the equivalent of this here. Proxy admin dot upgrade and call. So we're basically connecting with the owner. Then what we're doing in the upgrade and call function is passing. We can see the proxy, so the address of our existing proxy, the address of the new implementation to replace the current one with the new one, and then any arbitrary optional initialization data if required. And also in the implementation B, in this case, we don't have any initialization function to initialize post-deployment of the contract. So again, here we're passing the empty initialization data, and to check if everything went correctly, now we can query again the version and see that it is returning the version B, which is from the second implementation contract. If we want to also check if state is maintained, we can also see the other test cases. We can perform values, and here, let's see, get double. Yeah, there you go. So once we upgrade, again, we have the new function that wasn't available in the previous contract, in the previous implementation. So if we query get double value, now it correctly returns the value of 42, meaning that setting works and also obtaining the new functionality works too. So we have successfully upgraded our proxy to a new implementation. So this is the transparent upgradable proxy, but developers have also seen that all this complexity and overhead for the proxy admin maybe is not required, and we can actually move it to the implementation contract. In fact, the UUPS standard, or the Universal Upgradable Proxy Standard, is another pattern for proxy upgrades that introduces a new feature, a feature whereby the upgradability actually resides now in the implementation and not in the proxy anymore. Meaning that the proxy can be bare bones. We can simply use the ERC 1967 standard for the proxy, of which we saw the transparent upgradable proxy inherits from. And this way, we can have simply implementation contracts and the bare bones proxy as our entire architecture. The pros to this, obviously, is less overhead, less gas costs, because we don't have to check if the caller is an admin or not. The proxy is a lot simpler, and upgradability logic is inside the implementation contract, making it a single point of control. But obviously, this introduces a con, which is that if we mess up the upgradability business logic in the implementation contract, then we risk on actually being stuck. We risk on not ever being able to upgrade our proxy ever again. So let's see how this works again back in our source code. Let's go to the proxy folder, UUPS, and here we can see that now we just have two implementation contracts because we'll be using the ERC 1967 proxy as the proxy of our pattern. Now let's look at the implementation here, and we are introducing some new concepts that are very important around initialization. So to correctly implement a UUPS implementation contract, we need to implement some functionalities that are around the UUPS safety upgradability pattern. In fact, OpenZeppelin offers one of their abstract contract in their upgradable contracts library, which is the UUPS upgradable abstract contract. And here we can see that the proxyable UUID function is exposed. This is a way to diminish the risks of not having basically the upgradability business logic in a new implementation. In fact, thanks to ERC 1822, this standard defines a way to check prior upgrading to a new implementation if the new implementation logic at least has the functionality for future upgrades. Nothing prevents a malicious maybe implementation to override these functionalities and make it so that it's not possible to upgrade. But at least with this standard, we know that the functions required for upgradability are there. And these functions are the upgrade to and call public payable virtual function, meaning that we can also pass native currency to this function. And what it does, it checks for authorization. So it checks if the caller is allowed to perform the upgrade. And usually what is suggested is to override this authorized upgrade function with the business logic to check if the caller is allowed. In this case, we're simply putting the only owner modifier that we saw in the previous lesson with the ownable access control method, meaning that we check if the caller is actually the owner of the entire architecture. And if he is, then he's allowed to perform the upgrade. Let me go back to UUPS upgradable here. So if the authorized upgrade passes, then we actually call the internal upgrade to and call UUPS function. Here is where the magic happens in terms of safety checks. So we're looking at the new implementation if the implementation holds the proxyable UUID function and returns the correct implementation slot, which this implementation slot is defined by this constant here. So this is a way to check at least if the implementation logic has the functionality for upgrading, but obviously it doesn't check if those functions maybe are overridden into a way that it prevents. But it's a step at least in mitigating this big risk, let's say, in moving upgradability to the implementation contract. So the benefits obviously is a lot simpler architecture, single point of control, bare bones proxy, but you have obviously these risks. The vBetaDAO, for example, smart contracts suite thoroughly utilizes the UUPS standard and has these checks with the Open Zeppelin libraries. Also, if we look again in the implementation contract, we can see two new concepts here. We can see that the constructor is calling an initial internal disable initializers function, and also we have this initialize function here. So what disable initializers does, you can also read here to know the finer details of this, is simply disabling the target contract, so in this case, this implementation contract, to be able to be basically initialized directly. Because we know that the storage resides inside the proxy, meaning that we don't want our implementation contract to hold any initialization data when it is deployed. So this disable initializers simply disables the possibility for the implementation contract to be initialized in its own context, but must be initialized only through a call that happens from the proxy. And the initializer basically modifier here specifies which function is allowed to be initialized through the proxy. And in this case, what we're doing is simply setting through the ownable init, which is a way for upgradable contracts to be initialized post-deployment, who is the owner of this contract. So it's very simple in terms of higher level understanding, because it's like performing the constructor operations of a non-upgradable contract, but it needs to happen in a different way post-deployment because of the fact that the implementation contract is attached after it's actually deployed and pointing from the proxy contract. So in this case, we're simply specifying that the owner of this contract is the message.sender, so the caller of the proxy deployment, and allowing obviously the fact that the proxy holds the storage of this value instead of the implementation contract. Implementation B instead, in this case, is not a new contract, is not a completely new contract, but it extends from implementation A. So this showcases a way whereby we're extending the functionality of implementation A with a new contract and adding also a new storage state variable. So we can see here that we had already a uint256 value, and now we're adding a new uint256 value, which is called extra value. We can notice that this value comes before in terms of sequential order to the extra value. And this is not just a case. This is very important because of the fact that if you mix storage state slot positioning of values, you risk obviously on overriding previous values and therefore corrupting even your internal storage of your proxy. So it's very important to always append your new storage state variables of upgraded contracts at the end of the existing storage state variables. To facilitate this process, there are standards like ERC 7201, the so-called namespaced storage layout that is very much used also in the vBETA contracts, which allows to have a single struct that holds all your variables, so you can easily append there. It also specifies a storage slot that is a very, let's say, reduced collision possible storage slot in the EVM. And it's a series of best practices in order to prevent cases where you're overriding or creating storage state variables in positions already written, basically. So we'll also be looking at best practices around proxies after, but back to us regarding the implementation B. Again, here we're disabling initializers, but we're also initializing again our contract, our proxy, because the implementation B now holds a new value, and we want to set that value post-deployment. In this case, we can notice that the modifier is not initializer anymore, but it's reinitializer. It's simple, like it's similar to initializer. In fact, initializer is like reinitializer version 1, but the key difference with the initializer is you can use it multiple times in constructors, but in our case, it doesn't make much of a difference. It's more utilized for version 1 contracts. With reinitializer 2, basically we're saying, okay, I've already initialized version 1, but I want to reinitialize again, and I'm passing the version, meaning that if I, for example, in version 3, reinitialize with version 2, it will revert because I've already initialized my proxy the second time. So you need to specify basically the version of your implementation contract in order to correctly reinitialize. And the standard also here is to specify initialize with the version of the implementation, but this can differ based on developer preferences. In the case of this initialization function, we are passing an extra value, and this extra value is being stored, again, not in the context of our implementation contract, but in the context of the proxy. And this is also prevented through the reinitializer modifier. So I know it's a mouthful of things, but let's see this in simple terms, how it works with the UUPS proxy test suite. So again, in the deploy proxy fixture, we can have again our main actors, the owner, user 1, and user 2. Then here we can deploy again our implementations. So we are deploying the implementation A and deploying the implementation B, and we'll be deploying our proxy pointing to implementation A first. The key difference here we can see is that the proxy is now deployed with some initialization data. This is the part where I was saying that before, here in the transparent proxy pattern, we can see that there is no initialization data because we're not performing any calls post-deployment to the implementation contracts. Whilst here, because we have some initializer, for example, we're setting the owner of the contract. We're then also in implementation B, we're setting the extra value in the storage. We need to encode the initialization function correctly in order to pass it in the proxy deployment or in the proxy upgrade. So in the case of the proxy deployment, we can see here that we're passing the init data, which is encoding initialize, in this case, without any parameters. We can see, in fact, that in implementation A, the initialize function doesn't have any values passed as parameters, so we don't need to encode any values. Otherwise, it would be basically an array of sequential values, order based on the parameters of the initializer function. Once we have the init data encoded, then we can deploy our proxy by specifying, again, the implementation address, and in this case, also the init data. And then the fixture also returns the proxy attached to the various implementations for type safety based on the different ABIs of the two implementations. To check that everything works correctly, we can see that initial deployment happens that the owner now is the owner address because we called the initialize function. We can see here the initialize function that sets the owner of our contract. And we can see that also get value works and returns 0 because we have not set any value. 0 is obviously the 0 value of uint 256. Instead, if you want to set a value, we can do that easily by calling the proxy attached to the implementation AABI, setting the value to 42 and checking that the value now is 42. To upgrade, very similar to the transparent upgradable proxy, in this case, what we're doing is calling the proxy, instead of calling a proxy admin contract, we're directly calling the proxy attached to the correct implementation ABI and calling the upgrade to encall function. This is the public virtual function we saw inside the UUPS upgradable abstract contract of OpenZeppelin. And that contract performs all those checks we saw that the new implementation, in this case, implementation B, has the proxyable UUID function, has the authorize upgrade function, and returns the correct storage slot that is part of the standard in order to correctly upgrade and at least mitigate the risk of not having upgradability business logic in your implementation contract. And in this case, we can notice also the init data is different. We need to specify the new initializer function, which is this one here. And also in this case, we have a parameter to pass, which is the extra value. So we're passing that as an array. And because we only have one parameter, the array has only one cell. The upgrade happens. So instead of deploying, we already deployed the proxy. Now we're just simply upgrading and calling. So upgrading to this implementation address and calling the initializer v2 function with its values encoded through this encode function data helper function. So now we can check the new functionalities. We can check that we can still set a value because implementation B extends from implementation A. We can get that value. We can now get the added functionality, which is the extra value. And we can see it's 100 because it was set upon upgrade. And we can also get the new sum values function, which is here. We can see we have some values, we have set extra values, and we have the extra value here, which is public, and therefore we can access it like this because it's a getter. And then we also have other tests here to check if state is maintained and all the edge cases possible. So yeah, this was the UUPS standard. And key difference again with the UUPS standard with the transparent proxy is that implementation logic resides in the implementation contract itself and not in the proxy, meaning that we have less gas costs because of less overhead in the checks inside the proxy about the caller, whether to redirect to the proxy admin or to redirect the implementation contract. Now, last but not least, we have the third proxy standard, which is the so-called diamond proxy standard that comes after years of discussions, auditing from the EIP 2535 Ethereum improvement proposal. So what is the diamond proxy standard? The diamond proxy standard is, again, a upgradable proxy standard, but in this case, imagine that you have multiple implementations. You don't have only one implementation that you switch around. These implementations are known as facets, the facets of a diamond, basically. And the facets are built in a way through the diamond proxy to be able to share the same storage and to be able to be called based on the specific function a user wants to interact with. Why create or utilize the diamond proxy architecture? It solves a series of complexities. First of all, it allows for a granular, more modular, flexible approach to Solidity smart contract architectures, meaning that you don't have to have everything in one single implementation contract that maybe extends from different contracts and creates a lot of unreadability and complexity. And second thing is it solves, well, it doesn't solve, it mitigates one of the key limits of Solidity, which is the smart contract size limit of 24 kilobytes, meaning that if our implementation address exceeds the 24 kilobytes, we're not able basically to deploy that contract. Whilst with the diamond proxy, because we can split our logic in multiple implementation, multiple modules, and if a module requires even more granular modularization, we can do that. We theoretically have infinite, let's say, storage limits in terms of the architecture of the diamond proxy. How this works is that the diamond proxy now has a fallback function that is very, let's say, intelligent, because he's able to identify based on a function signature that we're interacting with, which facet, which target contract to delegate, call, and execute the business logic for that specific function, because we have multiple implementations. And to be able to basically shape our diamond, this happens through the so-called diamond cut functionalities. It allows us to add, replace, remove facets, implementations. And the diamond is built in a way that each facet shares a common shared diamond storage. And this is built in a way to be very flexible. And we'll see through the utilization of a new construct, a new particular, let's call it contract, which are Solidity libraries. And we look at also at Solidity libraries soon, how they work and what are their nuances. So before we dive into the Diamond protocol architecture in terms of source code, what are the pros and cons? Again, pros are we have a modular approach. It's all easier to handle large code bases. It's easier also to read and understand what facet, like what's the primary function and logic for specific facets and why it has its own module. And we can drastically reduce deployment costs. Instead of having, monolithic smart contracts, we can have a granular approach and deploy and switch around maybe a single facet or replace a single facet based on needs like new features or bug fixes, etc. Obviously, part of the cons we'll see is a really high complexity in terms of architecture. Managing storage can become quite tricky, but there are some standards in place we'll see to make that as easy as possible. And obviously, it's harder to audit because theoretically you have exponential explosion in complexity of the architecture. So without further ado, back to our code base, proxy folder, diamond, and here we can see already that we have different elements to this. First things first I want to tackle is the diamond library. So here we can see libdiamond is the core, the nucleus of our entire diamond architecture. Here we hold both storage management and core functionality for the entire diamond proxy pattern. What we can see here is the shared diamond storage I was talking about, and this diamond storage is a series of storage state variables that allows for association between function selectors and facets and the position in the facet for that function selector. We have which are the function selectors given a specific facet address, known as also target or implementation address. We also know which are the facet addresses, so all the facets that are part of the diamond proxy architecture. We also adhere to the ERC 165 standard, so we know which are the interfaces supported by the entire diamond architecture, and we can also save the owner of the entire protocol. In this case, it's like an ownable contract, but this can be easily switched around with role-based access control mechanisms like we saw in the previous lesson. To access this diamond storage, what we're doing is utilizing this internal function. This function allows us basically to point to the position of the diamond storage position, and the position is obtained by this hash here. So we're basically hashing this string, and the result is a bytes32 hex value. And this hex value points basically to the first slot of our diamond storage. And from there, basically all values of the storage state diamond storage are set in a way that we don't have conflict of storage. Obviously, if we define another storage position in the same exact position, then that would create overriding and potentially storage data conflicts. And obviously, this is not suggested. In fact, we'd see after the diamond proxy pattern some best practices around diamonds, proxies to avoid these scenarios. Then we have some ownership functions. If you want to set the new contract owner, who's the contract owner, enforce the contract owner when performing a transaction. But after this, we have basically the core logic around the diamond cuts. Just a reminder, the diamond cut is a core functionality of the architecture. It allows to replace a facet, add a new facet, or even remove an existing facet. And how this happens is by specifying an array of facet cuts. So a facet cut is defined, let's quickly open the interface here, is defined by the facet address, so one of the implementation contract addresses, the facet cut action, whether it's adding, replacing, or removing a facet, and the array of function selectors of that specific facet. So which are the specific functions that we can call to then basically specify through the mappings we saw in the diamond storage, which facet to point and which facet to delegate the call and execute the correct business logic. So back to our diamond library. So given the array of facet cuts, we then iterate through these, and based on the action, we call an internal add, replace, or remove handler. And if you obviously have time after the lesson or in your free time, have a look exactly at how these handler functions are updating the diamond storage variables and data in order to correctly map out function selector, facet, addresses, supported interfaces, etc., etc. One last thing here is we can see two more variables, two more parameters in the diamond cut standard, which is the init address and the call data. Imagine this basically as another smart contract. For example, here we have the diamond init, and this smart contract basically specifies a centralized and controlled way to initialize all our facets after the deployment. It's similar to the ones we saw before, because with the transparent upgradable proxy and the UUPS standard pattern, we had only one implementation contract, so it was easy to simply call the init data on that implementation contract. Instead, in this case, it's preferable. Now, it's not, let's say, an obligation, but it's preferable to have a separate contract that therefore defines all the initialization logic, because potentially you are handling multiple facets, you're doing multiple diamond cuts. So it's better maybe to have everything in one place and test that out to see if there are any reversions, any errors that are happening. So this is one of the best practices around the diamond cut standard. So yeah, this is the diamond library. It holds, again, all the core functionality around the diamond. And the diamond pattern also comes with two facets out of the box, let's say, that are must implementations. One is the diamond cut facet. This simply invokes our diamond cut in the library. Because we can't directly interact with the library, we need an implementation contract to invoke the functionalities of that library. So first we're checking, in this case, if the caller is the contract owner, and then we're performing the diamond cut with the same parameters that we pass in the diamond cut library. And then we have the diamond loop facet. This is now this is also another facet we must implement, and this is fundamental to basically offer readability. It's like a facade. It's a way to expose how the diamond architecture is modeled. So you have a getter around facets. It returns all the facets part of the diamond shape. It returns all the function selectors of a given facet. It returns all the facet addresses. It returns the facet address given a specific function selector, and also it returns a supports interface to check if an interface is supported by our protocol according to the ERC 16165 standard. Then before we look at now the facets that are actually part of our protocol, in this case, we created a simple game-like environment whereby we have a token, like an in-game gold currency maybe. We have NFTs, maybe, I don't know, it's like swords, shields, costumes, whatever. Before we look at those, I want to quickly show you the actual diamond proxy and how it differentiates from the transparent upgradable proxy and the barebone ERC 1967 proxy. So the diamond proxy differentiates in those because what it requires out of the box upon deployment is actually specifying one of its facets. And that facet is the diamond cut facet. Because the diamond cut facet, as we saw, holds the logic of the diamond cut function that therefore is able to update all those mappings and variables of the diamond storage. So in this case, what we're doing upon deployment is not only setting the contract owner, but performing the first diamond cut. This diamond cut is adding the diamond cut facet. And to do so, all you have to do is specify an array of cuts, in this case, only one element. And that element is basically a facet cut with the diamond cut facet address, the facet cut action of adding a new facet, and then all the selectors of the diamond cut facet, which in this case is only one because it's a diamond cut function. And back here, and to obtain that selector, all we have to do is reference in Solidity the interface the diamond cut function and get the selector. Then last but not least, in the constructor, what we're actually doing is performing the diamond cut operation by invoking the library reusable function and specifying the cut here. We can also notice that address, like the second parameter and third parameter, are basically the 0 values or empty string. This is because we are not initializing anything after the diamond cut. Instead, when we actually add the other facets to our diamond, in that case, we'll be invoking the diamond init and calling all of these operations through this init function. Let's now look at how actually the delegate call happens. So back in our diamond proxy, we can see again the fallback function is defined, and this fallback function doesn't point now or doesn't delegate calls to a single implementation address, but has to actually obtain, based on the message.sig, which is the function signature we are invoking, which facet to point to. So that is obtained through the selector to facet and position mapping inside the diamond storage. And to obtain the storage, what we're doing is referencing the storage slot position, as we saw in the diamond, in the diamond library here. We can see here diamond storage position. We are saving the diamond storage in this exact position here and getting the diamond storage position through this function here. And once we have that and we obtain the correct facet based on the function selector we are invoking, we can then perform the secret source of proxies, which is the delegate call by passing the correct facet implementation here. Whilst with the other implementations, transparent and UUPS, we saw that here it was the single implementation contract pointing that was basically connected with the transparent or UUPS proxy. And so last thing before we look at the tests, we saw all of these components that are part of the diamond proxy standard. Now we can look at actually the facets that we want to add that are part of our actual protocol. In this case, we have, for example, a game NFT facet. So this is a facet that handles logic around minting NFTs, transferring NFTs. This is a simplified version of ERC 721. We have the game token facet, also in this case, a simplified version of ERC20. It has name, symbol, decimals, total supply, balance of, and a function to transfer your balance from yourself, obviously, to another account. Then we'll see also how upgrading or replacing an existing facet with another one. So in this case, we'll be replacing our game token facet with a version 2, whereby this version overrides or redefines the transfer logic with the introduction of a with a fee. In this case, we're burning 1 token every time we do a transfer. And then we'll also see with the addition of a new facet, in this case, a staking facet, how you're going to actually add new facets to a proxy that has already been initialized with with facets and has already been initialized with it, in this case, diamond init smart contract. Hopefully, all of this is not too complex. Let's see with the diamond proxy test suite exactly how all of this is put together and connected with each other. So in the diamond proxy test suite, we can see again with our deployed diamond fixture how everything is deployed and connected together. So as we said, before deploying our diamond proxy, we need to actually deploy the diamond cut facet. This is the facet that allows to perform the diamond cuts, therefore adding new facets, replacing, replacing, or even removing existing facets. But in this case, the diamond cut facet will allow the fact that the diamond is initialized with the diamond cut facet, and then we can add, as you can see here, the other facets. So first thing first, we deploy the diamond cut facet. Then once we have the address of the diamond cut facet, we can now deploy our diamond by specifying the owner. So this will set the owner of the entire protocol in the diamond storage to the EOA, in this case, the first signer of our hard hat signers array. Then we're specifying the diamond cut facet address. We wait for this to deploy successfully. And now once we have our diamond cut facet in place and correctly attached to our diamond proxy, we can now perform the diamond cuts to add all the other diamond facets. So we're going to be deploying the diamond loop facet, which is the facade we were talking about. We're deploying also the ownership facet. This one handles the ownable part of the entire protocol, the game token facet, the NFT facet, and also the smart contract that will allow us to perform the initialization post the deployment of the implementation contracts. Here we actually build all the different cuts to perform on our diamond, all the different manipulations, additions in this case, of the facets to our diamond. So we define our facet cut enums. In this case, we'll be using the add action. So we are specifying the facet cut to add, in this case, the diamond loop facet. So we're specifying the diamond loop facet address, the facet cut action add, so addition. And as function selectors, we're actually extracting all of the function selectors of this specific facet. And to do so, it's very simple through ithers. All we have to do is iterate through all the functions from the interface of, in this case, the diamond loop smart contract, and push the function selector. But what is a function selector? Again, the function selector is simply the first 4 bytes of the hash of the function signature. So it sounds complex, but simply given a function, for example, this one here, the function signature becomes this one you can see here as a string. And then we're performing a hash of the function signature and slicing the first 4 bytes. It's from 0 to 10 and not 0 to 8 because the first 2 values are 0 hex in the case of hex strings. Therefore, we have to slice from 0 to 10. And the result basically is a 0 hex value. And this value is the function selector of the transfer function. So what we're doing here is transforming all of our functions into function selectors and specifying those in the specific cut, in this case, of the diamond loop facet. Then we add also the facets remaining, so the ownership facet, the game token facet, and the NFT facet. So these perform the same exact things. We're adding the selector based on the interface of these contracts. And once we have the cut array, so the sequential manipulations that happen on the diamond, we are actually able to perform the diamond cut. But before doing that, we're also encoding the init call of the diamond init function. So this is similar to the initialization, but we're handling it through a smart contract that has all the initialization logic between, as you can see here, the diamond storage, the game storage, which we'll see soon what is the game storage, which allows us to basically set the values of both the token facet getters and the NFT facet getters. So we're encoding here, as you can see, the values of the diamond init, so these values here. And once we have the encoded init function, we can finally perform the diamond cut, adding all the remaining facets. So we get the diamond with the diamond cut facet API, and now we perform with the owner the diamond cut by passing the cut, the diamond init address, so the contract where the initialization function resides, and the init function encoded correctly, again with the encode function data ethers helper function. Last but not least, we can even test out the transfer ownership. This is already set upon deployment. This is an example that you can even transfer after deployment. And we can also see the test suite here. Let me again isolate this quickly. That all tests are passing. What the tests are actually doing is checking if the values are correctly set with the initialization function after the diamond cut. Then we are also checking the token behavior, but what I want to show you here is adding new facets. For example, imagine I have, again, the staking facet here that allows us to stake or unstake our game token balance, basically. And what I want now is to add this facet, so this new functionality. All I have to do is deploy the staking facet. I have its address, specify the new cut here. So the facet address is the staking facet. The action, again, is the face cut action add. And the stake selectors are the ones that we have obtained from the staking functions with the interface. And then, again, we can perform the diamond cut by connecting with the owner of the entire protocol, specifying the new cut object here. And in this case, we're not initializing anything post cut, so post addition of this new staking facet. So we can simply specify the 0 address and 0 hex value because we don't need to initialize anything after the diamond cut. Now we can connect with our diamond as staking and see if everything works. So we can transfer, perform some stakes. So we're transferring from the owner to the user one, performing staking with the user one, checking again, now if the user can stake more than his balance, this reverts. And then we're also checking if the staking amount is correct. Also verifying if unstaking works and if balances are correctly updated. So all these facets are correctly connected to our diamond. We can see that different facets are being invoked based on the function selectors that we're calling, and everything is working smoothly and as expected. So the architecture is quite complex, yes, but it allows for these incredible use cases in Solidity that were unimaginable even 4 or 5 years ago. In case of replacing a facet, in this case, as we said, we want to replace our game token facet with a new version. So we're replacing our token with a updated transfer function in this case. All we have to do is specify, deploy the new version of the facet. And in this case, specify the replace facet cut action. So it's the second value of the facet cut action. Specify again the new token facet version 2 address and the facet version 2 selectors. And what will happen through the internal handler of the diamond library, it will replace for the same selectors, basically the new implementation address in order to have the correct mapping when calling the updated transfer function. Now let's attach again to diamond, the diamond with the version 2 implementation and call basically transfer. And we can see here that if we transfer 100 tokens from the owner to user one, the user one has 100 tokens, yes, but the owner now doesn't have 900, but he has 899 because the new transfer function, as we saw here, basically is adding a burn of 1 token as, let's say, a new feature that we wanted to introduce. And the total supply, because we burned this, is now instead of 1,000 is 999. Last but not least, regarding the diamond proxy pattern is removing a facet. So let's say we want to remove the game NFT facet that is already attached. All we have to do is perform a new diamond cut. In this case, the facet address is now the 0 address per the EIP 2535 standard. Basically, when you're performing a remove diamond cut, you just have to specify as the facet address the 0 address. Then the action now becomes the facet cut action remove, which is the 2 value. And now we are removing all the selectors basically of the NFT, the game NFT facet from the diamond storage mappings of function selectors to facets and vice versa. So we perform the diamond cut and now try, for example, to invoke a specific function of the game NFT facet, and we can see that it reverts with the custom diamond error, which is the function does not exist. Awesome. So this was an overview on the diamond proxy. Let me quickly go through also best practices. Now, I'll be sharing after this lesson, again, the recording, the presentation of the previous lesson and this lesson. And once I merge also the code base of the previous lesson and this lesson with the existing code base we had for the first 2 lessons, we'll be sharing that, that also, so you have everything in one place. If you want to also look at the differences between the standards we've seen, here's a fun little table showcasing exactly why you would need one instead of another. And let's also go through the proxy's best practices in order to not fall into corrupt data or not upgradable contracts if you decide to go for proxy pattern upgrades. First of all, for obviously large protocols, it's better to break up your logic into multiple implementations to not risk on having maybe limits on the contract size, or in the future adding new functionalities exceed the implementation, the single implementation contract size of 24 kilobytes. In case of the diamond proxy pattern, always initialize your diamond proxy with a valid diamond cut facet, because as we saw, that's the key part upon deployment. If it's done incorrectly, then you risk on having basically a diamond proxy unusable or with malfunctioning business logic. Then when adding new state variables, as we said before, always append those variables. So always have those variables at the end of existing variables. And to simplify that, there's the ERC 7201 namespace storage layout standard that defines some standards and best practices towards this. And it involves obviously the utilization of a struct. And in this case, as you can see, these new variables are appended at the end of already existing state variables in a previous version. Obviously, avoid state variables outside of the struct. In this case, the app storage is basically the game storage library we saw here. So one common practice is having a separate library or a separate struct to define all your variables that are outside of the scope of handling the Diamond proxy architecture. So in this case, we are saving the ERC20-like data, the NFT-like data, and as you can see, once we deployed the new staking facet, this basically was not present. So the idea is basically to add at the end of the struct the new mapping if needed in order to be able to deploy the staking facet. And yeah, next tip here is to avoid structs inside of structs unless you're 100% sure that that internal struct will never change. This is because storage slots in Solidity are contiguous. So if you add a struct inside another struct, and that internal struct maybe in the future through upgrades is changed or adds new storage state variables into it, you risk on corrupting your existing storage because everything is contiguous. And then adding new basically storage state variables to that, you risk on having basically storage state slots conflicting between each other. So one solution could be using structs with mappings, because mappings are handled in a different way. They don't point to contiguous slots, but they point to completely different slots. And the localization of those slots are obtained with specific ways the EVM handles that. I left also in the resources ways to read and understand better how storage slots are handled by the EVM. Now, sixth, let's say, advice is to avoid adding state variables in struct arrays. So if in your storage you have, for example, an array whereby the type of the elements of the array is a struct, you should never change the, let's say, composition of that struct. Otherwise, you risk obviously on having your contiguous data of the array again corrupt because obviously the element itself has changed what values it contains. Obviously, unique storage slots, like we said before, never point two different storage slots to the same position in the EVM. Otherwise, you risk obviously on having corrupt data and data overriding between each other. And last but not least, remember to protect your initialize function in the implementation contract, like we saw with the disable initializers and the initializer modifiers. And obviously prevent facets or implementation contracts from having like the self-destruct. Self-destruct is a low-level function called Solidity, which allows basically to remove the bytecode of that smart contract from the storage saved in this global computer of the blockchain, and also allows you to basically transfer all the ether left in that contract to another address. But why is this important? It's important because in the case, for example, of contracts that have upgradability built into them, you're not able to upgrade anymore, or function business logic is not available anymore. So a best practice is to avoid self-destruct in those implementation contracts and audit that there are no self-destruct calls that can be harmful for the proxy architecture. So last thing, we also mentioned about libraries with the Diamond proxy, but I also wanted to go a bit more in detail around libraries. Hopefully, yeah, we have a bit of time left. The libraries are basically what I call the cheat code for cleaner contracts in Solidity. They are special types of contracts, and they're very useful for reusable logic. And the key thing of libraries is that you can't really interact with them directly, but they're used for embedding inside existing contracts and utilizing the same logic without having to basically copy and paste between different implementations. So again, why you use libraries? For code reusability, but you can also use libraries for those implementation contracts, or in general contracts that are almost or exceeding the Solidity smart contract limit, because with libraries, you can externalize the bytecode to libraries, of course, which is an external contract at the end of the day, diminishing the bytecode that goes inside the implementation contract. One key thing to allow this, though, is that library functions need to be marked as external or public, basically. Otherwise, if they're marked as internal, what happens is actually the functions that are marked as internal are embedded inside the calling contract that utilizes the library. So this is a fundamental difference between the internal and external functions of library. Also, some other nuances is that libraries can't hold Ether, and they cannot have a payable fallback function, obviously, that passes the native currency of the blockchain. Quick look at libraries. Again, we saw the Diamond library, which is a very complex implementation of the library standard, and it allows, again, the core logic of the entire Diamond protocol to work seamlessly. But to look at a simple example, now in the libraries folder, we can see that my contract is a simple contract that is utilizing two libraries here, the strings library and the math library. What we can see here is also a very special syntax known as the using A for B syntax, whereby A is a library and B is basically a struct or a primitive type. In this case, we're extending this type with the functionalities of the libraries. For example, libstrings has a compare function, simply compares the hash of two strings to check if they're equal, and starts with checks if a specific string has a specific prefix at the beginning of the string, obviously. And in the case of libmath, what we're doing is allowing for double the value and half the value. So as you can see here, if we are using this using A for B syntax, what we can therefore perform is on the strings, these new functionalities like string item name now has the compare function, so we can compare the item name with cool item. So this returns basically true if the item passed is equal to cool item. Item has prefix instead checks if the item name pass starts with the sword prefix, and instead double value and half value for the uint in this case are extending with the double value function and half value, therefore allowing us to perform operations on this primitive type that didn't have these functionalities out of the box, therefore doubling the value that we pass or even halving it. To see how this works in action, let's go in our My Contract test suite for the library tests. And what we can notice again here in the deploy contract fixture is that here we're only deploying the math library. Why? Why is this? Because basically, as we said before, if we define functions in the libraries that are external, then the actual library is deployed in a separate address. It's like its own special contract. Instead, if we define functions that are internal, these functions will be embedded inside the bytecode of the using contract. So inside the bytecode of my contract. And that's why here, as you can see, we only need to deploy the math library and not also the strings library. So once we deploy our contract, we can see that basically our contract has all the functionalities of both the math library and the string library defined by its ABI here. But here I wanted to also show you exactly how the linking happens. So we can see, because we had to deploy the library, the math library as an external special contract, we have to link basically our contract to that library. Because what happens behind the scenes is that our contract now will be performing actually delegate calls to that library, in the case of the math library, to perform the logic of double value and half value. Instead, for the string library, those are directly embedded inside the my contract because the functions are internal. Therefore, there is no linking required to the libstrings library. And just to quickly see how everything is working, for example, here we can see that prefix is working. And instead, it should reject if the prefix is not stored. And also for the, we can see here for the math operations, if we double the value, it's correctly returning the correct value. So we can see that both libraries are connected. One is through linking and one is through embedding. Yeah, so that's basically it in terms of upgradability and libraries. Again, here you have all the resources if you want to take your time and read through everything we've talked about today, go more in detail. And I added also one bonus around gas optimization techniques. Here it explains it explains many different techniques and patterns and very particular nuances about Solidity and the EVM that you would think, wow, how is this possible? Like, for example, immediately, like the first example here is this is basically less efficient than performing this, and it explains why around all these gas optimization techniques. And also libraries, even more complex examples, like in the vBETA contracts, we have all our governors that are using UUPS standard, yes, but utilizing also libraries for diminishing the contract size limits, also creating a modular approach. And maybe in the future, we'll also consider the diamond proxy pattern for new contracts. Who knows? Yeah, that's basically it.